So in the last lecture, we talked about the simple harmonic oscillator. And at the end, we say that we have this eigenstate n, which are the eigenvector of the number operator. This number operator, if you try to think about that, it comes from the raising and lowering operator, right? It is A dagger A equals to N. I hope I'm right? Instead of A dagger, right? And the reason of this is due to the anti-commutation of the A dagger A actually, or the X and P, right? The fact that the two operators does not commute with each other, not anti-commutation, I say the wrong thing. They don't commute, right? The commutation property. The fact that they don't commute give rise to the 1/2, right? And then also, and then you have the 1/2 ground state energy. But we see that for this eigenvector, if you try to find its FH momentum or the expected momentum or the expected position, it is all 0. It doesn't look like a simple harmonic oscillator going from left to right. What I'm showing you here is not N. It's actually something called coherent state, which is a superposition of all these eigenvector and weighted by this, right? And it turned out that this one is the eigenvector of the lowering operator or annihilation operator, right? Which I asked you to prove in your assignment. Try to prove it yourself, right? It's easy to find from Wikipedia or anywhere, ChatGPT. I think you will get the answer right away. This is a typical textbook question or even textbook example, right? But really try to understand how, at least the skill, right? If you want to go further. So this is coherent state. So this is a spelling. It should be coherent, not coherence. Coherent. Or coherent state. Actually, I don't know. Coherent state. Okay, anyway. Maybe you can check. Now, and then we say that even for the electromagnetic field, you can do a similar quantization. The math is very profound, very confusing. That is not the purpose of this class, right? So you don't need to really understand. But I really hope you can try your best to understand by correlating the EM wave to quantization to the simple harmonic oscillator. And particularly, we say that this alpha and alpha dagger comes from the Fourier coefficient in the Fourier expansion of the magnetic field into the eigenmodes. Right? Remember, the magnetic field can be a superposition of different k vector, means different frequency. There's a different mode, different spin, right? It's circular polarized, right? You can say spin left, circular right, left or right, right? Or we call it spin 1 or spin -1 for the photon. We promote those coefficients becomes the operator. Now, if you forgot what I said, that is very normal. But I hope that you will have a feeling. I say, okay, there's a coefficient. I promote it to an operator. I hope now you ring the bell just like in the simple harmonic oscillator. We have X and P, which is a just variable. We promote it to operator, right? Something like that. But this A coefficient corresponds to the raising and lowering operator in the simple harmonic oscillator. And of course, we can again come up with a generalized coordinates and generalized momentum for the EM wave, which will obey this commutation relationship. Just like what we did earlier, X P equals to I H bar for a regular quantum problem. Yeah, question?
Based on that constant right there, wouldn't Q and P have the same units? But one represents coordinate is a generalization of it's displayed or the coordinates, and the other one is momentum.
Do they have the same units? Yes. But because when we say generalized momentum, it doesn't mean that you have the momentum unit, right? So yeah, you are right. Unless I did something wrong, they have the same unit, and indeed their unit is square root h bar. This go back to the first class. I talked about the G, right? Remember, someone asked me what is the units of G, and at that time we actually look at this number operator, right? Number operator has no unit, and it turned out this raising lowering operator also unitless. If we try to analyze it, yeah. So their unit is square root h bar. I mean, not the same as square root h bar, right? And that's why when you multiply, it becomes h bar. So you're right. So in this case, they have different units, x and p. You multiply to get h bar. I never thought about this, but I think you're right. Very good observation, right? So yeah, so that's important thing. The generalized momentum and generalized coordinates doesn't have the same unit as the real momentum and real coordinate. Good point. Make sense? Okay. If okay.